I wanted to solve this problem that involves a pulley here, a string or cable or wire that's wrapped over the pulley here. And on the left-hand side, there's a mass attached to the left-hand end of the string. And on the right-hand side, there's a mass attached to the right-hand end of the string. And the mass on the left, I've called it M1, and it's 0.52 kilograms. And the mass on the right, I've called it M2, and it's 0.50 kilograms. So we got this arrangement of masses either side of the pulley, where one mass is slightly heavier than the other mass. The one on the left is slightly heavier than the one on the right. So what's going to happen is, well, gravity is pulling both these masses towards the center of the Earth. There's a gravitational pull on the mass on the left, M1. There's a gravitational pull of the mass on the right, M2. And the pull on M1 will be slightly larger because it's got a little more mass. The pull on M2 will be slightly smaller because it's got a little less mass. And the end result is that M1 will accelerate downwards under gravity and M2 will accelerate upwards under gravity. We'll see that M1 accelerates downwards with an acceleration that's a small fraction of gravity, and M2 will accelerate upwards, again with an acceleration that's a small fraction of gravity. And we're going to calculate that acceleration. So the question here is that I want to answer is, what is the acceleration? What is the acceleration of the left hand and the right hand masses once we release these? The way I would start this problem is by sketching the forces. Specifically, I want to sketch the forces that are acting both on the mass on the left and on the mass on the right. So for the mass on the left, there's actually two forces that are acting. There's a gravitational force downwards, and there's a tension force due to the string upwards. And likewise, for the mass on the right-hand side, there's two forces acting. There's a gravitational force downwards and a tension force upwards. And for the mass on the left, those two forces of gravity and tension will add up to create a net force that causes the acceleration downwards of that mass. And the two forces on the right, the gravity and the tension, will add up to make a net force on the mass on the right that creates its acceleration. And so we want to picture all of that. So let me start with gravity. So this arrow is meant to indicate the gravitational force, let me call it the weight, of the left-hand mass. And this arrow is to indicate the gravitational force on the right-hand mass. So I called them W1 and W2 to distinguish them. And it's not quite clear from my drawing, but the gravitational force on the mass on the left must be slightly larger than the gravitational force on the mass on the right, because the mass on the left is a little heavier. The mass on the right is a little lighter. Then in addition to those forces, there's also tension forces. Let me draw the tension forces. They act along the length of the string. So upwards here for the tension due to the left-hand string, we're going to call that T1. And also upwards over here for the tension in the right-hand string, we're going to call that T2. And so those are the two tension forces. And so these forces, the gravitational force and the tension forces, add together for each of the objects and create a net force. And that net force is the acceleration according to Newton's second law. So F equals ma. So over on the left-hand side, I'm going to draw the acceleration. The acceleration will be downwards. I'll call it A1. And over here on the right-hand side, the acceleration will be upwards. I'll call it A2. And it's simply because the mass on the left is slightly heavier, the mass on the right is slightly lighter. So this mass wins in the sort of game for who gets pulled by gravity the most. This mass on the right loses in the game of who gets pulled by gravity the most. And so because the mass on the left is pulled down more, the mass on the right is pulled down less, the one on the left accelerates downwards, the one on the right accelerates upwards, because they're attached by the string. So those are the accelerations, and those are the forces. And we're going to solve this problem by applying Newton's second law to this arrangement, in which we have two masses, each experiencing two forces and accelerating. Now, there's a key point that I want to make here about these forces and accelerations. First point is about the tension. So the string leaves the left on the mass on the left, is wrapped around the pulley and attached to the mass on the right. That string is transmitting a tension force. And that tension force transmitted by the string is the same on the left and the right-hand side. So although I labeled them T1 and T2, T1 is equal to T2, and we're just going to call it T from now on. So the tension forces are the same because it's just a single string that's wrapped around the pulley. Second point, the accelerations. The accelerations downwards over here on the left-hand side is actually also the same as the acceleration upwards over here on the right-hand side. Again, because the objects are attached by the string. So however much the object on the left moves down, that object on the right must move up. So the accelerations, or at least the magnitudes of the accelerations, A1s and A2s, they're also the same, and I'm just going to call those A's from now on. So that's an important point. One last important point, and that's to do with when I write down equations, the signs of quantities in the equations. Now, if one way you can think about this problem is that it's really motion of the masses along a line. So the mass on the left is moving downwards along a straight line. The mass on the right is moving upwards along a straight line. And what we're going to do is call this direction from the right-hand side up over the pulley and down the left-hand side. We're going to call that the positive direction. So the acceleration over here, A1, that's an acceleration downwards, so that's the positive direction. The acceleration over here, A2, that's an acceleration upwards, but it's also the positive direction. So counterclockwise around the pulley, the string moving counterclockwise around the pulley is going to be my positive direction. And that's going to be how we're going to denote the directions of the accelerations and the tensions and the weights in this problem. Okay, so let's set up a nice picture. It's made a few statements, important statements about tension, acceleration, and the weight. So now let's do the calculation. To do the calculation, all I'm going to do is write down Newton's second law for the mass on the left and the mass on the right, for mass 1 and mass 2. So for mass 1, the sum of the forces that act on mass 1 are equal to the mass times the acceleration for mass 1. So that's Newton's second law. And I'm just going to write it out for the particular forces that are acting in my example here. So there's the weight, there's the tension force. Those are the two forces that act on mass 1, and they add up and create the acceleration of mass 1. Now, this plus sign for the weight is because it's acting in the positive direction, downwards on the left-hand side. This minus sign for the tension, T1, is negative. It's negative because it's acting clockwise around the path of the string. It's acting in the negative direction. And so that's how I got the signs here. And the acceleration, that's acting in the positive direction. So this is a plus m1a. So that's one equation, and that's for mass number 1. I'll just call it equation number 1. And then we're going to apply Newton's second law for mass number 2. So here's Newton's second law applied to mass number 2. It's the sum of the forces acting on that mass determine the acceleration of that mass by F equals ma. And all I'm going to do again is fill in those forces, and so that there's weight, and there's the tension force, and those two forces add up to make the net force, which determines the acceleration. And you'll notice again, when I put in the signs of the different quantities, I put them in based on my little sketch here, and what is the positive and the negative direction. So for mass number 2, the weight is in the negative direction. The tension is it's upwards over here on the right. It's in the positive direction. And the acceleration, that's also in the positive direction. And so I was careful about the signs. So here I've made two equations that contain the weights and the tensions and the accelerations, and I want to solve for the acceleration. And at this point, this becomes a problem, a mathematical problem of solving two equations for two unknowns. So let me just rewrite the equation. So here are the two equations in which I've just replaced W1 by M1G and W2 by M2G. And it's these two equations that we're going to solve for the acceleration of the left hand and the right hand mass. And there's a quick way of solving these for the acceleration. And maybe you can see it if you just stare at these two equations. Supposing I take the two equations and I add them together. What I mean by adding the two equations together is I'm going to add together the left-hand sides. And I'm going to add together the right-hand sides to make a new equation that has the sum of the left-hand sides and the sum of the right-hand sides. Since the old equations, the left and right, were equal one another, the new equation, the left and right, must still be equal one another. But what happens when you do that, we'll see, is that the tension, the unknown tension, cancels out. And we make an equation that we can use to solve for the acceleration. So let's go ahead and do that. I'm going to add the left-hand sides over here now. So I'm going to get M1G minus M2G, or I can rewrite it a little more compactly as M1 minus M2 times G. The tension, which is negative in the first equation, positive in the second equation, cancels out in that sum. On the right-hand side, I'm going to add together the M1A plus the M2A. And again, because A is a common factor, I can simplify it by pulling A out. And look what I've made. This is fantastic. I've made an equation that says if I divide through by the sum of the masses, that the acceleration of the left-hand mass downwards and the right-hand mass upwards is equal to the acceleration of gravity multiplied by a fraction. Fraction that's just the number, has no units, has no dimensions, and that fraction is just the difference in the two masses divided by the sum of the two masses. And since we know the masses, we can calculate this fraction. Let's do that. Here's the acceleration of gravity. And the fraction will be, well, m1 is 0.52 kilograms. m2 is 0.50 kilograms. So this is 0.02 kilograms in the numerator. Divided by the sum of those masses, that will be 1.02 kilograms in the denominator. And so this number here, we'll look at it, it's about 2%. And if you calculate the acceleration, you then get a number that's about 2% of the acceleration of gravity. It's roughly 0.2 meters per second squared. And so, like the incline, you could think of the incline, and Galileo thought about the incline as a way of diluting the acceleration of gravity, and you could do then do experiments on gravity. This pulley system with these two masses that are nearly equal masses, but not quite equal masses, it's also a way of diluting gravity. And you could imagine doing experiments on the falling of bodies on a pulley to investigate gravity. And we've slowed down gravity with this arrangement of two masses on a pulley from 9.8 meters per second squared acceleration down to 2% of that, 0.2 meters per second squared. And so it's easy then to see the fall with constant acceleration of the mass on the left, or the rise with constant acceleration on the mass on the right. It would not be easy to see them fall under the full acceleration of gravity. Anyway, just to conclude, this is a problem of forces. This is a problem of the relationship between forces and motion, acceleration. This is a problem involving two types of forces, tension forces and weight forces that we've discussed. And it's a problem where we analyze the action of the forces, relate it to the motion of the objects, and solve for the acceleration of the two masses. And so it's a very nice example, it's a very nice illustration, and it's a useful example in an illustration of Newton's second law of motion.